Hello everybody. Today I'm going to explain the problem F, Ehab's last theorem, from the Codeforces round 628 division 2. This problem was chosen by the users from my Discord server as the first problem of the day. And it turns out that this problem is quite interesting, and even though it seems hard, it's actually not that hard to come up with a working solution. Now let's move on to the problem. We must find an independent set which has exactly square root of n vertices, or we must find a simple cycle of length at least square root of n, and the graph is guaranteed to be connected. If you don't know the concept of DFS trees, which is required for this solution, please check out this blog. The link will be in the description. Now let's move on to the solution. The first observation which must be done in order to solve this problem is that you can't find just an independent set or just a cycle. There will be cases when only one of them is possible. Like, for example, if we have a complete graph, we can't find an independent set bigger than 1. However, if we have a tree, we can't find a cycle. So, this means that our solution must include dealing with both cases. Now I'm going to show you some trees, and what does this mean? Basically, for both trees, I showed with the continuous white line the main edges which form the DFS tree, and with dashed lines the back edges. If there are back edges, there will always be cycles, and if there are enough back edges, we will always find a big cycle. Why does this work? Well, it's quite easy to observe it, like intuitively speaking, that if we have many edges, they are going to connect many nodes between each other. And since the DFS tree has just n-1 edges, if you have many edges, it's quite likely that you will end up finding at least one big edge. And also, the nodes must have enough neighboring edges in order to do it. Here I showed with orange axis one such cycle, and with green axis another such cycle. Both cycles are good, and they are bigger than square root of n. However, this is not the case for all the trees. In this case, you can see that we have only one cycle, which is of length 3 and not big enough for our tree with 10 vertices. However, since we didn't find a long enough cycle, you can observe by intuition, using something similar to the first case, that we are going to have a sparse graph. And since we have a sparse graph, which is still connected, it's quite likely that we will find an independent set which is long enough. In this case, I managed to find an independent set with length 5, but there are obviously bigger and better options, like instead of 5, we can just take 8, 9, and 10. However, we are not required to find the biggest independent set. This is an NP-complete problem. But we only have to find just an independent set of length at least square root of n. This seems quite intuitively, and I will show you that it's not hard to implement either. In this case, I'm going to show you how to use the DFS tree in order to actually implement what I said before. The implementation of the DFS tree looks similar to the one used for big connected components, which are also used for finding cycles in undirected graphs. Basically, if we didn't visit vertex, we will just add it to our DFS tree, and the edge between the current node and its neighbor will be a main edge in the DFS tree, and the level of the uh, neighboring vertex will be bigger than the level of its father by 1. However, if we found a back edge and it's long enough, we're just going to print the last uh, edges on the path from the level of the neighbor to the level of the node. If we found a back edge, this means that the level of the neighbor is always smaller than the level of the node. Since we are keeping the path from the root to our node in the stack, the reconstruction of the path is quite easy. Now, what if we don't find such a cycle? If we didn't find such a cycle, as I presented previously, the graph is sparse. And this means that we can find an independent set easily by uh, doing something similar to bipartite matching. Basically, if our vertex isn't marked as not eligible for our independent set, we're just going to mark its neighbors as uneligible. And it turns out that we can always print at least square root of n vertices, as the problem requires us to do. If you liked watching this video, please like it, subscribe to the channel, and press the bell button in order to be the first one to watch the new videos. If you want to be more in touch with the Problem of the Day project, please join my Discord server, which always has updates regarding my videos. Until the next time, good luck, stay safe, stay healthy, and goodbye.